Everybody, my name is Carlo Harvey, and I'm here to talk about the integration, the multi-sensory integration of sound, graphics, and smell. As a very simple observation, when we think about virtual environments, and specifically quality in virtual environments, we think of it as parameterized by lots of different things, a myriad of things that influence our perceived quality in that environment. It could be shading, it could be geometry, it could be resolution, it can be frequency in both sound and light, it can be particle effects, it can be a myriad of different influences over what we see and perceive. So that quality, when we consider those different parameters, and indeed many other parameters, can be parameterized as a function. And equally, when we consider computation in that, computation of that quality that we deliver to a user is also parameterized by the resource that's available to us, what budgetary constraints we have. So when we think about this problem, specifically we want to think about how much importance do humans give to graphics in virtual environments? How much importance do humans give to acoustics in virtual environments? When we think about virtual environments, obviously they're scene dependent, the scenes change. Equally, how much importance do we give to smell in virtual environments? How much importance do we give to different smells? Is there a hedonic tone complex there? And when we think about the resources that are available to us, how does that mapping of our preferences in those different domains change as we go from a low resource to a high resource? So here's the problem that we're facing. How do we go about doing that? Now, Dinesh mentioned that the Xbox provided 10% of one core for acoustic computation, which is a little bit cheeky, but ultimately this is what they go about doing. They assign arbitrary values to this because intrinsically we don't yet understand it. And that's what we're hoping to draw some illumination onto today, if at all possible. But in the area of smell, specifically olfactory computation, we don't really know too much about just noticeable differences. In fact, in a lot of terms, we could say we don't really know too much about how we even smell. There are various different camps in that from a perceptual point of view and a physiological point of view as well. So we devised an experiment that looked into computing the dispersion of smells in virtual environments from a source position, that's the blue objects in these virtual environments, given some deviation in this environment, so the red objects are fans, or they could be heat sources, or they could be open doors with wind blowing into the area. And we emit until we reach a certain condition or criteria of concentration at a receiver's point, which are these green objects in these spaces. So we looked at solving the Navier-Stokes equation to gather the concentration at all of these different control volumes in these spaces. Now, these control volumes are effectively the limit on computation for this domain, because we have to solve this differential equation for every control volume in this space. And specifically, this control volume dictates how accurate we can be in this virtual environment, how accurate we can be about the concentration that's delivered to a user from that olfactory perspective at every point in space. And this is just showing it in a different scene as well. So gathering these concentrations over time in these virtual environments, we can get an accurate representation for different discretizations of that control volume in that virtual space to reach a continuous set of that control volume. And what we want to do is investigate across that computation differential how human perception is influenced by the concentration that's been delivered in that virtual environment. Specifically, what we wanted to do is investigate where just no noticeable difference occurs across known smell sources, in this case, citral. So we developed an olfactory display, two digital mass flow controllers are controlled by an air compressor, and they can deliver specific intensities in a range of 1.2 to 11 parts per million, and that's going to be very accurate within that range. We have a laptop that people are allowed to give rating conditions for, and participants sit in front of the olfactory display. Now, we used a methodology, a pedestal versus varying methodology, where effectively we're delivering certain smells in parts per million to a user and asking them to rate against another smell that's delivered subsequently. So it's two interval forced choice. For anybody who's actually had durian, I'm not sure the taste is worth it because it's incredibly smelly, but what we wanted to do was explore the bounds of this olfactory device, this olfactory display. We wanted to look between 1.2 and 11 parts per million and sort of establish just noticeable difference and see if it matches up with Weber's law, so we can use that more conclusively in this computation task. So for each participant, we delivered a baseline starting from the very lowest C-min of this olfactory display, 1.2 parts per million, and explore this interval in steps, delivering different intensities to a user until we got a criteria of rating above a 75% threshold and map that to a psychometric function. If we found a just noticeable difference within that domain, we then stepped that step change and looked within, again, the display's range all the way up to 11.2 to establish baselines of just noticeable differences of these parts per million in this olfactory domain. So the task was very simple, was smell these two smells, tell me which one smells more, right? And they were given a task to effectively rate or pick which one they thought was stronger. When we had a 75% threshold, or noticed the 75% threshold of accurate judgments, we could establish a baseline as a just noticeable difference. And what we noticed was obviously at C-min, which is 1.2, the lower bound of the olfactory display, and all the way up to C1, where we had this 75% threshold of correctness, we had a just noticeable difference within the bounds of the olfactory display at 2.3 parts per million. So we then stepped onwards through the olfactory display's domain and looked all the way up to 11. And again, we found another just noticeable difference at 9.8, which from the previous just noticeable difference at 3.5 was a 6.3 parts per million step. And that matched quite closely with Weber's law's approximations for smell. Now, the caveat to this is obviously this changes depending upon our hedonic tones of particular smells. We grow up and we've got evolutionary principles that we can smell certain smells at the part per billion level, like fire and smoke, because we don't want to get caught in a fire, right? Makes perfect sense. So there is a caveat to that, but citral was fairly well known as a smell and had all of the parameterizations that we could feed into the Navier-Stokes equation, so it serves as a very good baseline here. But what was really interesting, actually, was when we explored the different control volumes in the computational fluid dynamic solver, was it doesn't actually matter. Because over time, in each of the conditions that we tested, for control volumes of 1K all the way up to 1 million, we found that, in fact, that part per million level didn't matter in that virtual environment. If we've got a just noticeable difference at 2 or 3, and we've got just noticeable difference at 6, we're looking at the difference of 6 minutes here at the bottom, and we're only seeing deviations of 1 or 2 parts per million over that time. And when we look across the different complexity of the solvers, it doesn't make a difference, which is quite nice. So we stepped on and looked at developing a different experiment, which looked at how we map, or how humans map, their sensory allocations across vision, graphics, and sound and smell. And obviously, when budgetary constraints are here, we think that maybe graphics would dominate. When we have medium-level resources, we think acoustics might fit in. And when we have high-quality resources, does smell fit into this system as well? And does computation get assigned accordingly to these domains? So we had a second setup where participants could effectively assign normalized computation to these different sensory domains given certain budgetary constraints. So we developed a number of different budgets for each of these 3 senses. And for each of these senses, we had a number of stimuli, images. And these were all boiled down eventually. We set up with 240 across the range of what we could see, all the way from 16 by 9 to UHD, all the way from very low frequency to 352 kilohertz. And in the olfactory domain, because it was simply binary choice, we used the 1K control volume because we could use a smaller amount of computation. And we went with these, and we had normalized budgets and computation for each sense. And then we asked for each participant, playing with different budget levels, how would you assign the budget that's available to you to the computation in each of these domains? And obviously, because we're normalizing the computation, we're stripping away any algorithmic complexity of simulating each of these three senses. So the scenes that we had was a car, a kitchen, a church scene, and a bathroom. The church scene was reserved for a later validation step. So we went forward with the experiment in the initial phases with those first three scenes. So looking here, this is what the participant was asked to do. They effectively assign computation to each of these three senses in graphics, in sound, and in smell. They can turn smell off as a binary option, and they could effectively play with these until they're comfortable with that assigning of that budgetary constraint to these three senses. What we found was that across the smell domain and across the budgets, at very low budgets where not much computation was available to you, smell tended to be off across all three scenes. And as the budget increased, we found obviously smell being turned on as elements of normalized computation. Similarly, in the acoustics domain, as the budget was low, we had less than 10% actually. But it went all the way up, which I found really interesting because I sort of had sort of 75, 25 in my mind. It went all the way up to nearly 40 in the top level budgets. So acoustics was incredibly important in this virtual environment, which I found really, really powerful. And obviously as a result of that increase in acoustics, graphics has to come down across these budgets, but dominated in low budget environments, which was to be expected. But what we can see here is that when scenario and budgets are considered, actually the attribution of this computational resource on the participant level is pretty similar across low budgets and pretty similar across high budgets. So that's B1, B2, and B4, B5. And those groupings are effectively saying there's no significant difference between allocation of computation across those budgets or those budget levels. So across this observed information, we built a model, well, technically two models actually, because we found that there was scene dependence across those scenes that we observed. And so we thought we'd see whether an extra set of parameterizations, that's that scene level in the model there, helps us better encode the model on that scene level and whether there's a significant difference based upon that scene dependency. So we generated a standard model, M1, and also a scene-dependent model, M2. What we then did was look across these budgets, B1 to B5, and establish some new budget levels that we hadn't previously established and see if the model fit well to that. So we created MB1, MB2, and MB3, which are the midpoints of B1, B2, B2, B3, B3, B4, respectively. And so we observed that this model, the general model, fits relatively well with estimations in the accuracy range of between 3 and 7% across graphics and acoustics and smell. And the scene dependency, as you'd expect, fits even better. But what we wanted to go and do was go one step further and say, does this model apply generally to scenes that we hadn't seen before? Can we predict the computational allocation in a previously unobserved scene? And for graphics on the top right, for acoustics in the bottom right, and for smell in the bottom left, we can see that the M1 model, this green line, fits relatively well. However, the scene-specific model fits even better. But we've got a threshold tolerance of between 3 and 6%, again, still, even for M1, which is rather good. So the conclusion is we've looked at a little bit into how humans allocate computational resources across three senses in virtual environments, and specifically how this maps to different budgetary constraints. There are obviously limitations. We don't have dynamic scenes. We've not considered hardware implications of VR technology or hardware that introduces extra levels of immersions or presence. But ultimately, it's a fairly novel area, and so we're quite happy with what we did. Are there any questions?
One question. You showed us the JMD, which was supposedly for all users that you calculated it for. Was there any, if you look at individual differences between user performance and the budget that they assigned, the second part, were they the same users first of all?
Oh, okay. So the question was, for anybody who didn't hear, were they the same users across each experiment? The answer is no.
Okay, okay, the question. Okay. Basically, would you expect that users will assign a different budget based on their ability to differentiate between smells? That's what I basically wanted to ask.
Yes, so we consider hedonic tone to be incredibly important, and we think that would be one of the influences. And in fact, going back to this slide, what we noticed was that in the smell domain, actually the probability for this model was vastly different, and underestimated and overestimated, and we think that's due to the hedonic tone of the smell, because it's contextually relevant to the virtual environment that's being presented within.